Good evening to the participants.
Good evening, sir.
Yes. Welcome to the week 5 of live interaction session. The name of the course is Advanced Reinforced Concrete Design, and this course is brought to you by NPTEL. Yeah. So, uh, the course is being instructed by Professor Surya Prakash of IIT Hyderabad, and this interaction session is presented by me. My name is S. Lalit Sagar. I am a doctoral candidate and PMRF fellow in the Department of Civil Engineering at IIT Delhi, and I welcome you all, and I welcome the participants also who are going to watch this online later to this week 5 of the live interaction session. So, in the week 1, we studied the introduction to reinforced concrete structural systems, and in the week 2 we studied the material properties, and in week 3 we looked into the durability aspects of reinforced concrete structures, and in the week 4 we considered the design of analysis and design of axial members, and now presently we are in the week 5, and in the week 5 we are going to study the behavior of flexural members. So yes, the protocol for the live interaction session is going to remain the same. I hope that the participant has watched the week 5 of the lecture.
Yes, sir. We have watched.
Okay.
We.
Okay, so first of all, I would like to start off by asking if there is any doubts from that from this particular week of lecture, because it was little mathematically little more involved.
So far, we don't have any
Okay, ha-
particular questions.
have you attempted the assignment questions by any chance?
Oh, no, not yet. We have just watched.
Okay, okay, okay. Right. Yeah. So I hope that this session will be useful, and we'll keep on interacting as the session goes on.
Okay, sir.
Yeah. Yeah. So in this week we are going to have about 19 questions, and it will be a mix of both the theoretical as well as the numerical aspects of the flexural analysis and design, and about 25% of the questions would be theoretical, and the remaining 75%. As I mentioned in the previous live interaction session also, from now on the classes, the examples and the course is going to become more numerically oriented, and the calculations are going to be little more involved, and with an emphasis on the design aspect of reinforced concrete structures. So without any further delay, we will start the session. Yes, I hope that my screen is visible now.
Yes, sir. It's visible.
Yes, so as we did in the previous live interaction session, we are going to spend about 15 minutes on the uh, summary of the presentation that you watched in the course, and after that we are going to take up the examples. So in this module we are going to look into the behavior and design of flexural members, and this module has been divided into 5 parts. So first part is the background to flexural theory and moment curvature analysis. Then we are going to study the effect of concrete strength and reinforcement ratios on the moment curvature analysis. Then the effect of axial compression and compression reinforcement on moment curvature analysis. Then in parts 4 and 5 we are going to look into the flexural design aspects using the IS code. So for this week we consider the first 2 parts of this module. That is, we provided the background to flexural theory and moment curvature analysis, and then we studied the effect of concrete strength on the and reinforcement ratio on the moment curvature analysis. Okay. So the expected learning outcomes are we are going to explain the behavior of member under flexural loading. In the previous week we looked into the behavior of members under axial loading, so we'll try to understand what is flexure. Then we are going to study the elastic beam theory. Then we are going to derive the equivalent stress block parameters in order to perform the flexural analysis. Then we are going to perform the moment curvature analysis. We are going to see what a moment curvature analysis means and what we are trying to achieve through that. Then we are going to discuss about the different failure mechanisms under flexure. Okay, so essentially flexure is nothing but the bending. So if we consider a simply supported beam under a uniformly distributed load and a point load, so we are going to obtain a bending moment diagram something like this. So whenever there is an external loading, it manifests in the form of internal stresses, and these internal stresses are going to be expressed in the form of resultants, that is the bending moment and the shear force. And essentially the bending moment is nothing but it is a couple that acts as a it is just a couple which is formed because of the action of compressive and tensile forces at the cross section of the beam. So we are going to study how exactly these external loads are going to manifest themselves in the form of moment of resistance and the bending moment in this particular session. Okay. So when we consider a straight prismatic beam, so a prismatic beam is one where the cross-sectional properties are uniform across the length of the member. Okay, so when a bending moment is applied to a straight prismatic beam, so essentially we look into what happens to the longitudinal lines and the transverse lines. So these are the longitudinal lines and these are the transverse lines. So the longitudinal lines becomes curved, and depending on whether they are above the neutral layer or below the neutral layer, they undergo either compression or they undergo either the shortening or the elongation. And then the vertical transverse lines, they essentially remain straight, but they undergo some sort of a rotation. So this is an example of a beam which is having a circular cross section that is subjected to flexural loading, and this is the neutral layer. So the neutral layer or the neutral surface is one the longitudinal fibers of the material will not undergo any change in length. So depending on the type of bending moment that is applied, for example, if we are applying a sagging bending moment, that is if we are going to bend in this fashion in the pattern of U, then the top fibers undergo shortening and the bottom fibers undergo elongation, and the neutral axis is nothing but the intersection between the neutral surface and the transverse cross section. Okay, so we're going to learn more about this concept in the form of problems and numericals. Then, in order to develop the mathematical model for a beam under flexure, so we have to make certain assumptions. That is, the plane section normal to the beam axis remains plane after bending also, and the maximum compressive strain in concrete is taken as 0.0035. And as we looked, this particular module has been divided into 5 parts. So for parts 1 and 2, and even probably for part 3 also, we are going to consider the parabolic model. So in the previous models we have considered the Hognestad relation to correlate the relation between the stresses and strain within the concrete, and we have seen that it follows a parabolic model, and we have also seen the mathematical expression. And for the subsequent parts, that is parts 4 and 5, we are going to consider the stress strain curve that is based on the IS code, that is based on the different building codes and the design standards. And we are going to ignore the effect of the tensile strength within concrete when we perform the flexural analysis. So this is essentially the elastic beam theory. So we consider a simply supported beam, and we consider a very small infinitesimal length of this beam, and it is having a length of dx. And if we consider a fiber which is at a distance of y from the neutral axis, so that is defined as ds. And when it takes up a deformed configuration, as you can see, so since dx corresponds to the neutral axis, the length of the dx remains unchanged. However, because of the sagging bending moment at this particular cross section, the fiber which is at a distance y from the neutral axis, that undergoes a shortening from ds to ds prime. Okay, and essentially the beam bends as an arc of a circle, and this particular angle is given by d theta, and the radius of the curvature is given by r. So what we are trying to establish here is the relation between curvature and the strain within the beam. So the strain is expressed as the change in length over the original length. Okay, so we are going to define ds prime. Ds prime is nothing but r minus y into d theta, and dx is r into d theta. So we simply substitute these values of ds prime and ds, and ultimately we have the expression for strain. And here r is the radius of curvature, and 1 by r is nothing but the curvature itself. So if the expression for curvature, that is 1 by r, is also expressed as phi, the Greek alphabet phi, that is equal to epsilon by y. So epsilon, as we saw, is the change in the length of the longitudinal fiber, and y is the distance of the fiber from the neutral axis. Okay, so in the elastic beam theory, in the first part we established the relation between the curvature and the strain, and in the second part we are going to establish the relation between the curvature and the moment that is developed in the beam cross section. So this I hope that you have watched in the lectures in this week's lecture. So just to give you a summary, so we are going to take the component of stresses acting on this plane. This is sigma xx and this is sigma xy. So there has to be a correction in this. the symbol of this stress component, and here F is given by the axial force. Axial force is nothing but sigma xx into B into dy. So dy is the small strip that is having a height of dy considered in this cross section, and this strip as well as the beam has a width of b. Okay, so when you integrate the value of sigma xx multiplied by the area, the infinitesimal area that is being considered, and then when you integrate within the along the height of the beam cross section, that is minus h by 2 to plus h by 2, we obtain the axial force. Similarly, when you replace sigma xx by sigma xy, we obtain the shear force, and in order to obtain the bending moment, we need to consider the value of sigma xx into b into dy, and we need to multiply that by the value of y. Okay, so when we consider force into the lever arm, we obtain the value of the bending moment that is developed for that particular cross section. Okay, and when we substitute the value of epsilon, that is strain, and then after substituting and simplifying this particular expression, we obtain this particular relation between the curvature of the beam and the moment that is developed. So the curvature phi is equal to 1 by r is equal to m divided by ei. So here the term ei corresponds to the flexural rigidity of the beam. Okay, so the higher the value of ei, the more difficult it is to bend the beam, but if the value of ei is less, then it is said to be little more flexible, that is, it bends easily. Okay, so here we consider when we consider the the mathematical expression for curvature, if we consider the vertical displacement at this particular cross section as v, the value of curvature, that is 1 by r, is represented as d2v by dx square divided by 1 plus dv by dx square whole raised to the power 3 by 2. So since we are considering the value of dv by dx as almost 0, so when we square a small term, so the value of this particular term is almost negligible. So this entire denominator becomes 1. As a result, we are going to express the curvature 1 by r is equal to m by ei is equal to d2v by dx2. So this we are going to use in order to obtain the slope of a beam at a particular point. The slope of a beam is given by dv by dx, and we can find the vertical deflection at any point along the length of the beam, and this is given by v, and you will be solving one of the assignment problems based on this particular concept. Okay. Moving forward, so after we establish the relation between the curvature and the strain in the beam and the bending moment, then we are going to perform the moment curvature analysis. So what does the moment curvature analysis mean? So moment curvature analysis is simply the relation between the curvature and the moment that is developed. So if a beam undergoes rotation, or if the curvature is phi, then what is the moment that is developed? So we are going to plot for different values of curvature what is the moment, and this will help us to assess the flexural behavior of a beam. Okay, so in this essentially what we are doing is we consider the stress strain behavior of concrete under compression, and then since it forms a parabolic law, we are going to convert it into an equivalent rectangular stress block. So these the parameters alpha 1, beta 1, so these corresponds to the various parameters which are made in order to approximate this parabolic stress distribution into a rectangular stress distribution. So once we obtain the value of the compressive force and the tensile force within the concrete and reinforcing steel, then we can simply multiply it with the lever arm, that is the distance between the compressive and tensile force, in order to obtain the moment, and subsequently we can obtain the value of curvature also. So the curvature phi is given by epsilon c divided by depth of the neutral axis x. Okay, so in that way we are going to establish the moment and curvature for different strain values within concrete. So moving on, so in order to obtain these parameters, that is alpha 1 and beta 1, so alpha 1 corresponds to the multiplying factor that we need to incorporate along with f prime c in order to develop this equivalent stress block, and beta 1 corresponds to the factor that we need to multiply along with the neutral axis depth, that is x, which corresponds to the equivalent stress block. So these are some the integration that we need to perform in order to arrive at these values of alpha 1 and beta 1. So after so essentially there are two criterias. So in order to transform this parabolic stress distribution into rectangular stress distribution, so we need to consider two criteria. So the criteria one is that the resultant forces should be the same within this parabolic stress block and this particular rectangular stress block, and the second criteria would be that the location of resultant forces has to be same, that is the value of Cc, the resultant of this force which is at this particular height, has to match with this particular the distance of this particular resultant force, and upon simplifying we obtain the value of beta 1 as 4 minus epsilon c by epsilon prime c divided by 6 minus 2 times epsilon c by epsilon prime c, and alpha 1 is given by 1 by beta 1 into epsilon c by epsilon prime c minus 1 by 3 into epsilon c by epsilon prime c square. Okay, so we are going to solve certain numericals so that this application becomes more clear to all of you. So in the moment curvature analysis we are going to come back to this procedure, but just to give you a brief idea, so we have to take a particular value of epsilon c, that is strain within concrete. Then we need to assume a value of x, that is the depth of the neutral axis. Then we need to determine the value of resultant compressive force and the tensile force. So if these two are matching, then our assumption of x is accurate. We can go ahead and calculate the value of m and phi. However, if there is an imbalance within these forces, that is if c is greater than t or c is less than t, we need to modify the value of x so that these two forces match, and after these two forces match we can go ahead and determine the value of m and phi. Okay, so these concepts will be more clear when we solve the numerical problems. So essentially when we mean the moment curvature analysis, what we intend to develop is that we will plot the value of curvature and bending moment at different strain values. Then we're going to obtain this very nice moment curvature plots. Okay, so we discuss about the different types of flexural failures. So it can be either a balanced failure, that is balanced failure is when balanced failure is one where both the failure of concrete in compression and the yielding of steel in tension takes place at the same time. And we have the under reinforced beam, that is a tension controlled failure where there is yielding of reinforcing steel first before the concrete achieves its compressive failure. And then we have the over reinforced beam, that is the compression governed failure, where the concrete in compression crushes first before the steel can reach its yield strain. Okay, so we are going to discuss more about these in the upcoming examples that I have prepared for this particular week. And in the second part, again, it is just the moment curvature analysis for different types of cross sections. So again, we are going to be looking into this analysis procedure once again. So in example 1, we have considered a heavily under reinforced section. So I think the reinforcement is less than 1% of the cross section, and then we have developed the moment curvature relation corresponding to different values of strain within concrete. So we obtained this moment curvature plot. Then in example 2, we determine the value of area of reinforcing steel that is required to achieve a balanced failure. Then similar to the example 1, here also we have developed the moment curvature plot. Okay, I think the plot is, yes, so here is the plot. Okay, and then in example 3, we are going to see we saw the effect of compressive strength of concrete on the moment curvature relation. Okay, so this is the moment curvature plots. What happens when we change the grade of concrete from 20 MPa to 30 MPa to 40 MPa. So while we maintain the area of steel, what happens to the moment curvature relation when we vary the grade of concrete? Okay, so we saw that how by increasing the grade of concrete, the moment capacity does not increase significantly. However, the curvature increases, the curvature or the ductility. So ductility is essentially the ability of member to yield, to deform after its yielding. So as we can see, the concrete which is having a grade of 40 MPa, concrete cylinder strength of 40 MPa, that is able to undergo significant deformation after yielding, hence it is having a higher ductility. So we are going to discuss more about the moment curvature analysis. So I hope that now we are ready to start with the question and answer sessions. Yes, are there any doubts, or shall we proceed with the question and answers?
Sir, I have one question.
Yeah, please go ahead. Yes.
Does this moment curvature analysis
Yes.
holds true in the case if the beam is not simply supported, just like in a portal frame where the both ends are fixed? Can we apply this theorem? to analyze is the beam that is in the portal frame.
Yeah. So that is a, that is a very good question. Actually, this moment curvature analysis is relevant to any member irrespective of the boundary conditions. Okay, so it is
Okay.
just that we have taken this for the simplification, but whenever we are using a design software, like SAP or ETABS, so there is an option to develop the moment curvature relation. I hope you're aware of that, right?
Yes, sir.
Yeah, yeah. So it irrespective of the boundary condition, we need to have the moment curvature relation for any member. So yes, to answer your question, this particular analysis is relevant for uh, any structural member, whether it is a beam or a column. Okay,
Thank you,
and
sir.
yeah,
Okay, okay.
yeah.
Thank you so much.
So yeah, so we have the first question. So when a beam is subjected to flexure in a 2D plane, what happens to the longitudinal and transverse fibers? Okay, it is a simple problem on beam bending.
Option D, longitudinal fiber elongate and shorten, and the transverse fiber rotate.
Yes, thank you for the response. Any other participant would like to answer?
Sir, actually, I have doubt in assignment 4 questions. I will ask you later about this, about
Yeah,
that question.
yes, yes, sure, sure. Okay, so I think it is the answer is quite straightforward. So the answer is D. So depending on the location of the fiber in the cross section, above the neutral axis, the fibers that is when we consider a sagging bending moment. So yeah, so when we consider sagging bending moment, then the fibers above the neutral axis they shorten when and the fibers below the neutral axis elongate, and the transverse fibers rotate in the vertical plane. Okay, they remain straight. Yeah, so we can see that this particular beam is undergoing sagging because of this particular vertical load, and the longitudinal fibers they undergo shortening or elongation depending on the location above or below the neutral axis, and these transverse fibers they undergo rotation. They remain straight, but they undergo rotation. Okay, moving on to the second question. Which of the following statements is or are incorrect about the neutral axis or the neutral layer of a rectangular steel beam subjected to flexure? So there are multiple options for this particular question.
Sir, your screen is not visible.
My screen is not visible.
Now, just now.
Oh, is it? Okay, okay.
Now it is visible.
Okay, okay. How about now? Is it visible?
Yes.
Okay, okay. Yes. Please let me know if you are not able to see, so that I can adjust. So just to give the participants a hint, there are two incorrect statements in this particular in these four options.
Option option A and C.
Okay, okay. Yes. Any other participant would like to try?
B and C, I guess.
B and C. Okay. Okay, thank you for the response. We will move ahead, because we have some numericals also. So the correct option is option A and C. So I had played around with the words actually. So the neutral layer is a horizontal layer along the length of the beam. It's not a vertical layer, and it does not undergo any change in length. Okay, and the neutral axis is the line of intersection of the neutral layer with the transverse section. This statement is correct, and the position of the neutral axis in the cross section varies along the length of the beam. So this statement C is incorrect because the position of neutral axis remains the same along the length of the beam. And option D, locating the neutral axis is essential to determine the moment of resistance and curvature of a cross section. So this option is also correct. Okay.
So again, screen is not visible.
Okay. What about the other participant? Is it visible?
Yes, sir, it's visual.
Okay.
So now it is visible.
Okay. Okay. Yes. So yeah. So when the beam is not under flexure, the neutral layer remains horizontal. Upon the application of lateral loads, it bends as a curve. The length of the neutral axis does not vary. The position remains the same. So if we consider a cross section at this point or this point, the depth at which the neutral axis lies is same along the length of the beam. And lastly, as we saw in option D, the location of neutral axis is required in order to determine the moment of resistance and the curvature of a beam. Okay. Moving on. I hope my screen is visible.
Yes.
According to the elastic beam theory, the relation between longitudinal strain and curvature is given by, so you have to select the right option. R is the radius of curvature, epsilon is the longitudinal strain, y is the distance of fiber from neutral axis, and L, so this has to be capital L, okay, to maintain consistency between the question and the options. L is the length of the beam. Okay, so kindly select the right option.
Option D.
Okay. The other participant, would you like to confirm?
Yes, sir. But I have not seen all the lectures of week 5, so I'm not
Okay, okay, okay.
sure.
Yeah. Yes. So the correct option is option D. It is straight taken from the lecture slides. So we discussed about the derivation also. So one suggestion is that I strongly recommend that you try to watch the week's lecture, and also try roughly you can try to solve the assignment questions, so that you'll be better prepared, and you can actually make the most of this live interaction session. Okay, so that's just a small suggestion. And yeah, so the correct option is option D. So the curvature, that is 1 by r, is equal to epsilon by y. Okay, moving on. So in the last slide we saw the relation between the longitudinal strain and the curvature. So this pertains to the relation between the curvature and the bending moment. According to the elastic beam theory, the relation between curvature of a beam and its bending moment is given by, there are 5 options, so kindly select the right option.
Option B.
Yes, thanks
B
for the
only.
response. Yeah, so the correct option is option B only. Yes, so in order to develop these stress resultants, though the various stress resultants are axial force, shear force and bending moment. So this is based on the stress that is acting on this particular plane. We can determine by integrating these stresses across the cross section at any given length, we can determine the axial force or the shear force and the bending moment. So when you simplify this, when you plug the value of epsilon from the previous relation between curvature and strain, and when you simplify, we obtain this expression. And as you might be knowing, we also have the flexural equation, that is, I am sure you might have studied that in your strength of materials, that is sigma by m by I is equal to sigma by y, that is equal to E by R. Okay, so as you can see, we can just we can ignore this for the time being. So if we take the value of E and put it over here, we have the equation. So the curvature, that is phi, is equal to 1 by R is equal to m by EI. Okay, so moving on. Yes, so which of the following failure modes, flexural failure modes, are brittle in nature? So there is only one correct answer. Request you to point out.
Option E.
Okay,
B option.
option D, is it?
B.
Okay, B. Okay. Okay, option B is incorrect. Can you try once again, the participants?
Option E.
Okay. Yes, option E is the right answer, because as we can see in this lecture slide, I hope that my slide is visible. So as we discussed earlier, there are 3 types of failure. We have the balanced failure, we have the tension failure and the compression failure. So in a balanced failure, what happens is that when the beam bends, there will be the strains will be developed in the cross section. So the top fiber that is undergoing compression, so the concrete undergoes the crushing strain. At the same time, the steel in the tension region, that undergoes yielding. Okay, so the failure mode is brittle, and this is sudden, and it does not give any warning in the form of adequate deformation. Okay, so whenever we test this kind of beam in the laboratory, they fail suddenly. Okay, that is why it is called as a brittle mode of failure. And similarly, in the compression mode of failure, the steel reinforcement would not have undergone yielding, but the concrete crushes suddenly. So this happens in an over reinforced beam. So this is also a brittle mode of failure, because it fails before giving us any proper warning. On the other hand, if we consider the under-reinforced section, so that is under-reinforced section undergoes a tension governed failure, and as per the IS code, or in fact any other building code, that is the preferred mode of failure, because that gives us adequate warning before failure. And if a beam is designed for failure, then we prefer the tension governing failure over these two types of failures. So the correct option is option E. Okay. So we are going to move on to the the numerical problems, and I am sure that you will be having questions because the calculations are a little more involved. So I would like you to just try this problem. If possible, try to draw a sketch of this beam, and then we are going to discuss how to solve the problem. I hope that my screen is visible. Kindly try to solve this problem. So we are considering a reinforced concrete rectangular beam. It is having a width of 250 mm and total depth of 450 mm. The beam has an effective cover of 50 mm. So the effective depth is, that is small d, is 450 minus 50, that is 400 mm. The concrete has a mean cylinder strength of 30 MPa, that is F prime C, and the beam is reinforced with 4 steel rebars of 20 mm diameter, and the steel is of grade. It has a yield strength of 500 MPa. So if the concrete undergoes a compressive strain of 0.005, what would be the corresponding moment and curvature that is developed in the beam? So that is the question. You can take 2-3 minutes in order to solve this problem. Did any of the participants figure out the answer? I guess we can take another 2 minutes, then we can go ahead with the answer and the solution. Yes, I think we can go ahead with the solution. So I will just give the answer, then we can discuss how to go about this. So the correct answer is option B. So can I know what was the difficulty in the answering the question?
It was a iterative process, sir.
It was a iterative process, and which is why the calculations are a little bit involved. So it is extremely difficult to solve using pen and paper, right? So may I know, like, what was the value of x that was assumed from your side?
I assumed it's 85.
Okay, yes. Yeah, so as you rightly said, it is extremely difficult to solve this using pen and paper and a calculator. You need to write a program. I have used Excel sheets. Yeah, I hope that it is visible. My screen is visible, right?
Yes, sir.
Yeah. So yeah, I hope that you can see. I suggest that you develop this Excel sheet on your own, because one of the assignment problems for assignment 5 we have this you need to make use of this spreadsheet in order to solve the problem. So yeah, I will give you, just the basics of how to go about this. So we need to enter the width of the beam, that is 250 mm, overall depth to 450, effective depth is 400, then the value of AST is 1256.64, and the corresponding percentage of steel is 1.12%, F prime C is 30, epsilon prime C is 0.002, and Fy is 500. Okay, now we need to enter the value of 0.0005. Okay, so it is very small value of strain. So let me take you back to this slide as to how to perform the moment curvature analysis. So in order to perform the moment curvature analysis, we need to choose the value of epsilon c. In our case is 0.0005. Then we need to assume the value of x. So after that we need to calculate the compressive force and the tensile force. Only when the compressive force and tensile force matches, only then we can say that the assumed value of neutral axis depth is accurate. Then we need to go ahead and determine the value of m and 5. Okay, so yes, so we for this particular value, let me just reduce a little bit so that the value of compressive force is visible. Yes, so for this particular value of 271, the compressive force is 467 and the tensile force is 59. So as the value of C is very high, we need to reduce the value of X. Let us try 200. Okay, now it is 343. I hope that you can see the numbers clearly.
Yes, sir.
Okay. And the value of TS is 125, so we need to reduce it even further. Let us try 150. So again, the value of CC is higher, but it is somewhat converging. Okay, let us try 140. Okay, so we are closer. Again, let us try for 130. Okay, so now we have the value of T has exceeded, so I try a value of 138. So for 138 we obtain a reasonable match. Okay, so let us go ahead and try to perform the calculation now. Right, so yes, so let me start off by, I request you to pay attention now carefully. So if you understand this procedure, then the same procedure holds good for the rest of the session also. So step 1, we have to choose epsilon c. Okay, so epsilon c is 0.0005. Then I'm just going to write the serial number. Step 2, we have taken x is equal to 138 mm. Right, so we are assuming that it is going to, this is the strain distribution along the depth of the cross section. Okay, So this would be the neutral axis. Kindly bear with my poor handwriting. So epsilon c is equal to 0.0005 and epsilon t is what we need to find out. Okay, and the value of x is 138 and the overall depth is 400 mm, right? So by by the principle of similar triangles, we have epsilon c by x is equal to epsilon t divided by d minus x. I hope that it is clear as to why, how we got this equation.
Yes, sir.
Yes, so when we substitute and solve, we get a value of epsilon t as 0.00095. Okay, so let us consider the stress as ft, that is epsilon t into epsilon steel. Okay, so yeah, we get a value of, when you multiply it by 2 into 10 to the power 5, we get a value of 189.9, 89.9 MPa. Okay, so let us call the value of tensile force as Ts is equal to, Ts is given by F into T into As. So As is 1256.64, for which we obtain a value of 238.6 kilonewton. 238.6 kilonewton. Okay, so this is the value of Ts. Right. I hope that it is same. Yeah, so we have gotten the same value, 238.6 kilonewton. Okay, now we need to find out the value of C, that is the resultant compressive force. So Cc is given by alpha 1 into F prime C into beta 1 into X into B. Okay, so again I'm going to just write the expression for alpha 1 and beta 1 so that you can substitute later and check if you're getting the same, right? Since it's the first problem, I would like to so first we need to find out beta 1, because beta 1 is independent of alpha, but alpha, to determine the value of alpha, we need to find out the value of beta 1. Beta 1 is equal to 4 minus epsilon c by epsilon prime c by 6 minus 2 times epsilon c by epsilon prime c. Okay, so you can check it later whether you are getting the same value. You get a value of 0.6818. Okay, and for alpha 1 is equal to 1 over beta 1 into epsilon c by epsilon prime c minus 1 by 3 epsilon c by epsilon prime c whole square. Okay, so if we substitute again, epsilon c, you need to take the value of 0.0005, right? And epsilon prime c, we are going to assume the value as 0.002, right? And alpha 1, we get a value of 0.3361. Okay, so okay, so when we substitute it in this particular equation, we get the value of Cc as the value of Cc is 237.2 kilonewton, right? Okay, so after this we need to find out the value of m and phi. Excuse me, I need to accommodate everything here, so I'm going to find out the value of m and phi in this particular corner of the slide. Okay, so m is given by Cc into d minus beta 1 into x divided by 2. So we are going to multiply the compressive force with the lever arm, which gives us a value of 83.72 kilonewton meter. Okay, and we have the value of phi is equal to epsilon c by x, which gives us a value of epsilon c is essentially the strain in the extreme compressive fiber. We get a value of 3.62 into 10 to the power minus 6, and the unit is mm to the power minus 1. Okay, so yeah, the correct answer is 83.7 kilonewton and 3.62, right? Okay, yeah, I hope that it is clear for the participants now. Hello.
Yes, sir, it's clear.
Yeah, so I request you to prepare an Excel sheet. So I think your assignment is due by the end of this week, I think. So I cannot share the Excel sheet now, but I can share it next week. But I strongly suggest that you try to prepare on your own, so that you will be able to solve by yourself. Okay, so again, yeah, the procedure is quite straightforward. As we were discussing, I would like to go back to the so again we need to choose the value of epsilon c, assume the value of x. Okay, so based on trial and error, you determine the value of x, and then you calculate c and t. Only if c is equal to t, then we are sure that the assumed value of x, that is the depth of neutral axis, is correct. After that, we need to find out the value of m and phi. So when you when you calculate the value of m and phi for different values of epsilon c, ultimately you get the moment curvature relationship. Okay, so yeah, so the right answer is option B. So
Sir, I have one question.
yeah, please go ahead. Yes.
Is there any way we can calculate the relation between epsilon c that we assume in this question and the
Yes.
load applied on that beam? Is there any relation or any way to calculate
uh,
this thing?
yes, yeah, let me yes, yeah, absolutely. I think that's a very nice question. So yeah, so what we can do is like if we consider this I'm taking simply supported beam again because of the uh, convenience in the calculations, right?
Okay, so
Yeah, so let's say that it is being loaded by this particular any given load P. So since it's a determinate structure, statically determinate, we can find out the value of moment, maximum bending moment at this point, right? So we have the value of m. So again we can use the flexural relation, m by I is equal to sigma by y, right? So we can find out the value of sigma is equal to m by uh, I by y. So sigma is nothing but m by z. Z is the section modulus, and from here we can simply obtain the value of E is equal to I'm sorry, can yeah, so we can simply determine the value of strain as sigma by E. Yeah, and since we are dealing with a concrete beam, we can consider EC. I hope that this answers your question.
okay, sir.
Yeah, yeah,
I got it.
yeah, yeah. So essentially, I would like to add to your point actually. Like I wanted to discuss later on uh, regarding the point that you raised uh, earlier. Like earlier, the participant asked that if this particular m5 relation is same for if we consider a portal frame having a different boundary conditions, right? So what I would like to say is that in all the other undergraduate courses, what we do is let us consider that there is a rectangular beam and there is some sort of a steel reinforcement. So basically what we determine is just the value of the moment of resistance, or for from a design perspective it is determine the design moment of resistance, right, depending on the load that is being acting on the beam. Okay, but since it is this particular course we are it is a PG level course, so we need to not only determine what is the ultimate moment, but we need to find out uh, the ductility of the member also. So there can be one particular beam that is if this is the M5. Okay, so this is beam number 1. Okay, and then we have one more beam, that is beam number 2. Okay, so though the beam number 1 it might have slightly higher value of the moment. Okay, but we need to understand the curvature. As I was mentioning, the ductility is given by the ratio of the peak deformation, in this case curvature, to the yield curvature. Okay, so whenever there is when we are designing a structure, we need to design it to be adequately ductile. Okay, so it is not just the value of m that is required, we need to find out the value of phi also. Okay, so from that perspective it is really important that you understand the flexural behavior of a beam. Okay, because along with the moment of resistance we need to assess the ductility characteristics of the flexural members also. So whenever be it whatever structural member that we are considering, whether it is a beam or whether it is a column. So in the next week we are going to consider the behavior of beams along with the axial forces also. Okay, so it is merely it is we are merely changing, we are considering the support condition, but the moment curvature relation is extremely important. It is extremely important to understand the moment curvature behavior for any type of a structural element, whether it is for a beam or a column, or for even if we consider other forms such as the shear wall or whatever it is. Okay, yeah, so just wanted to add that one. So
Thank you so much, sir.
yeah, so I hope that we can consider, because again I think most of us we have the doubt, all we need is the the design moment and the ultimate moment of resistance. Why we need to calculate the why we need to perform the moment curvature analysis? So this is the reason. So in addition to the ultimate moment, we need to understand how it deforms. Okay, which is why this chapter becomes important. Okay, so I hope that the participants you are with me. Yeah, I hope the other participant is also he's able to understand the discussion.
Yes.
Yeah, yeah, again I think you would have been in a better position. I hope that if you're able to see the lectures of that particular week, I think we'll be in a better position to make the most of this, and that will help a lot in solving the problems for your assignment. Okay? Yes, on that note, we'll go ahead with the next one. So in the previous question we considered a strain value of 0.0005. Now what will be the value of moment and curvature corresponding to strain of 0.001? Okay, kindly take 1 or 2 minutes and see if you can obtain the value of x, neutral axis depth, because once you are able to determine the value of x, then the problems becomes very simple, very straightforward. Okay, kindly take 1 minute for this. So I will just give you a hint actually. So this was the previous question. So this is So I will ask a simple question. So in the previous question we had a strain value of 0.0005 and this was the curvature phi 1, and here we have a strain value of 0.001 and here is phi 2. So what is the relation between phi 1 and phi 2? Phi 1 is less than, equal to, or greater than phi 2?
Phi 1 will be greater than, phi 1 will be smaller than phi 2.
Yeah, so phi 1 is going to be smaller, as you rightly said. So since phi 2 is greater than phi 1, so this particular angle is slightly more. So if this is x1, the neutral axis depth, can you tell what would be the relation between x1 and x2?
2 times.
Not exactly 2 times. You can just tell whether it is less, equal to, or greater than.
Uh, x1 will be probably smaller than
Yeah,
x2.
right. So x1 will be smaller than x2. So we need to increase the depth of the neutral axis. From the previous question we need to increase the depth of neutral axis, and then we need to find out the proceed with the calculations. Okay, so again I would like to reiterate it once again. I will just give you a flow chart. Okay, so we need to assume, okay, let me take a different color just to break the monotony. So if you are able to just internalize this particular procedure, you can solve any particular problem, okay, related to this. Okay, but again you need to make use of the Excel sheet, so I recommend that you do it. So we need to assume the consider a value of epsilon c, then you assume a value of x. Okay, then you check whether it is c is equal to t. Okay, let me box it up. Okay, check whether c is equal to t. Okay, after this find out the value of moment. Moment is nothing but compressive or tensile force multiplied by the lever arm. Find out the value of curvature. Okay, it is simple 5-step process, but this becomes the most important, like this becomes the most important aspect. Okay, so if we are able to crack the value of x accurately, so that the value of c is equal to t, then all your calculation becomes very easy. I hope that this is clear for all the participants. Okay, so we will try to, actually you can help me to find to determine the value of neutral axis for this particular. Okay, feel free to participate. Okay, so the cross sectional properties are the same. We just need to modify the value of strain, that is 0.001. So yeah, you need to ensure that the value of cc is same as ts. So can you suggest the value of x over here, please?
180.
Okay, let's try 180. Okay, so the value of cc is very high, so we need to reduce.
160.
Okay, I will proceed as you say. Okay, so yeah, I request, I hope it is visible to the other participant also.
Yes.
Yeah, so you can suggest the value of x. so that both, let me highlight it, so that it becomes easier uh, for the participants. I think, yeah, I think yellow is good. Yes, so these two values have to be same. Okay, let me just, I'll highlight only that. Okay. Excuse me. Yeah, could you suggest the value of x once again? We need to balance the compressive force and the tensile force. Any suggestions?
Mm. 150.
Okay. Okay, we need to balance it further because it is 468 and it is 418.
147.
Okay, 147. Okay, so still we need to reduce. Let's try 145. Okay, still it is high. 146. Sorry. Okay, still it is high. Sorry.
143.
Okay, 144. 144 we are converging. 143. 143 is it becomes high, so we need to I got it at 143.6. Okay,
Okay.
so at this point we have balanced both the forces. We have the value of epsilon c, we have the value of x, and we know the value of alpha 1, we know the value of beta 1 also. So the corresponding value would be 156.9 kilonewton meter, and curvature would be 6.96 into 10 to the power minus 6. Okay, so the correct answer is option A, right? Yeah, so okay, I will just I will again, you need to again, you have value of epsilon c, then assume the value of x, then find out the value of epsilon t, that is strain in steel, find out the value of force in steel, that is ts, then you need to find out alpha 1, beta 1, those are the parameters for the equivalent stress block in concrete. Find out the value of cc, then you have to match both of these. Okay, after that find out the value of moment and curvature. Okay, okay, moving on. So we will again we need to find out the value of m and phi for a strain of 0.0015. Okay, let us go back to our Excel sheet. Okay, so here we are going to change it to 0.0015. Could you suggest what should be the value of x now? Should it be more or should it be less?
Less. 125.
No, I think we need to increase it because it is 605. We need to balance it with 628. Okay, so I got it for a value of 149. Okay, so for 149 we are getting almost same values, and the procedure is same. Okay, epsilon c to x, epsilon c, epsilon t, ts, force in the steel reinforcement, then force in the equivalent stress block of concrete. Okay, then find out the value of M and phi. So the correct answer is option D, that is 217 and 10.07. Okay, so yeah, we have M as 217 and phi value is 1.0067 into 10 to the power minus 5, or it can be expressed as 10.067 into 10 to the power minus 6. Okay, so we can go to the next problem. So we need to find out the value of M and phi corresponding to a concrete strain of 0.002. We will go to the Excel sheet. So I need your help once again to fix the value of X. Can you suggest the value of X here, please? So CC is 745.
Little bit more than that. 150.
No, actually the CC is high than TS, so we need to reduce the value of X. Let's try 145. Oh, it is still high. It is still high. I got the equal forces for a value of 125.6 mm. Okay, as you can see, we are able to balance the value of compressive force and the tensile force, and the corresponding value of M is 221.62 and phi is 15.92. 221 and 15.92. Okay, so the correct answer is option B. Okay, request the participant to kindly mute. Yeah, I'm sorry, I was having a bit of disturbance, so I requested you to mute. So yeah, moving on, finally we take a value of 0.0035. Okay, and yes, let us go back to the Excel sheet. We are going to take value of 0.0035. Okay, and the value of C is 686, so we need to reduce the value to obtain equal forces. Let us take 120. Okay, so still we need to reduce 115. Okay, so we are able to achieve very close value. Ultimately I got, for a value of 114.8, we are able to obtain almost equal values of equivalent compressive force and the tensile force, and the corresponding value of M is 218.7 kilonewton meter, and the value of curvature is 30.5 into 10 to the power minus 6 per millimeter. Okay, so it is 218.7, 217.7, 218.7 and 30.5. So yeah, so we have option D is the right answer. Yes. So after we obtain the values, so what we did from question number 6 to question 10 were that we assumed the value of epsilon c, then correspondingly we found out the value of phi, and then we found out the value of M. Okay, so corresponding to 0.0005, 0.001, 0.0015, 0.002 and 0.0035. We got certain values of curvature and m. Now we need to plot the curvature in x-axis and plot the m in y-axis. Okay, so we obtain something like this, right? So the beam, as the curvature increases, the moment also increases, and at this particular point, at a curvature of 10 into 10 to the power minus 6, it undergoes yielding, and after that it continues to deform. Okay, because the concrete can undergo additional strain after the steel has yielded, and we very well know that if we consider the stress strain diagram of HYSD steel bars, okay, so it undergoes yielding at this particular point, and after that it continues to elongate, to significant value of strain. So when we take up a beam and we consider, when we keep on loading it, right? So if we keep on loading it like P1, P2 and so on, so even after after the yielding of the steel reinforcement, it is able to undergo deformation in the form of curvature to a significant amount. So we are going to determine up to the ultimately this point corresponds to a concrete strain of 0.0035. So this is how we can develop the moment curvature plot. So as I was explaining earlier, so instead of just finding out the value of ultimate moment of resistance or the design moment of resistance, when we have the value of both the moment as well as the curvature, we completely understand the flexural behavior of a beam. Okay, this is why it is extremely important to understand this particular concept. Okay, I hope we can proceed to the next problem.
Yes, sir.
Yes, yeah, thank you. So yes, this I think we can solve without a computer program, so I request you to solve this. Okay, for the rectangular reinforced concrete beam given in question 6, what should be the area of reinforcing steel in order to achieve a balanced failure? Okay, okay, just because we are almost nearing the end of the session, I'm going to give you a hint so that you will be in a better position to tackle this problem. In fact, in the lecture slides or in the lecture also, sir has solved a similar problem, so I request you to just take this hint and try to solve the problem. So we can solve this problem by the virtue of the definition of what is meant by balanced failure. I hope I request the participants, to try this, using the hint that I'm writing on the slides right now. Okay, I think we can take another 30 seconds, then we can, proceed with the correct answer and the solution. Uh, were the participants able to find out the value of x based on this equation?
Yes, sir.
Okay, yeah, can you please tell?
233.33.
Yes, yeah. Thanks for the response. Yes, so yeah, I think we can go ahead with the solution. So what we are trying to do is, by virtue of the definition of what is meant by a balanced failure. So balanced failure is one where the yielding of steel occurs and simultaneously the concrete fails under compression. Okay, so the compressive strength at failure for concrete is taken as 0.0035, and the strain at which the reinforcing steel yields is considered as 0.0025. Okay, and by the principle of similar triangles, we write this equation: 0.0035 by x is equal to 0.0025 divided by 400 minus x. So here 400 is the effective depth. So we obtain the value of the neutral axis for a balanced failure for this particular section. Then in the second step, we need to equate the compressive force with the tensile force. So compressive force is given by alpha 1 into f prime c into beta 1 into x into p. So we know the value of f prime c from the previous question number 6. We know the value of x from the this particular calculation. We need to find out the value of alpha 1 and beta 1. Alpha 1 and beta 1, we have discussed the equation previously, and it is basically a function of f prime c and epsilon prime c. Okay, so it is a function of these variables. Similarly beta 1 also. So you can easily find out the value of alpha 1 and beta 1, and we know the value of b, that is the width of the beam, and we also know the value of fy, that is the yield strength of the reinforcing steel. So we need to determine the value of as. So as turns out to be 2552.1 mm square. Okay, yes, so so 2552.1 mm square. So this is the balance section. Okay, And for the balanced rectangular section, what is the moment and curvature at failure? So this can be done, you know, through hand calculation also, because we already know the value of you know, epsilon c, and we know the value of x. Epsilon c is 0.0035, and we know the value of x. X is I'm sorry, 233.33. From this we can find out the value of epsilon t, right? From this we can find out the value of, you know, the stress in steel. We can find out the value of the force, and we can find out the value of the equivalent stress block parameters alpha 1, beta 1, find out the value of cc, and then we need to ascertain whether both forces are equal. Ultimately we find out the value of moment of resistance and the curvature phi. Okay, so this can be done manually also, but to save, yeah, if the participants are able to calculate, kindly let me know. If not, I'll proceed with the
Option A.
okay. Option A is what I've answered. Yeah, thank you for the response. Let us check if it is right. So AST is, for this case, AST is 2552.1, and epsilon c is 0.0035, and the value of x is 233.3333 for better accuracy. And we see that, you know, as we saw, we got the value of 0.0025, that is the strain in steel at yielding, and the corresponding compressive force is 1276, and the tensile force is also 1276, so the forces are balanced, and the value of ultimate moment, that is 376, and the curvature at the failure is 15 into 10 to the power minus 5. I'm sorry, 15 into 10 to the power minus 6, and option A is absolutely correct. Thank you for the response. And now, as we read earlier, we are going to plot the moment and curvature values corresponding to different values of strain in concrete. Okay. Yeah, option A is the right answer. Okay, so yeah, I have done the calculations, and again, so as you can see in the earlier problem, okay, when the section was under reinforced, so what we saw that the moment capacity was lesser, right? Let me go back there. So the moment capacity was about 225, but it was able to undergo a curvature of about 30 into 10 to the power minus 6. But if we consider this case, okay, so it was able to undergo only this much value, but it was able to undergo sufficient amount of curvature. So this curvature is representative of the ductility. So this goes to say that it is not just the value of moment that is important. It is also important to ascertain the value of the curvature also. So we are going to see a comparison of under reinforced and balanced section and over reinforced in the subsequent slides. So I know that we are overshooting the time, but since we started the session at around 7:10, I hope we can extend up to 9, 10.
Okay, sir.
Yeah. So kindly answer this particular question. It is quite straightforward. For rectangular RC beam, what is the maximum permissible area of steel reinforcement that can be provided as per IS 456? Anybody would like to answer? Okay, so we will go ahead with the I thought it was quite straightforward. So the correct option is option E, right? It is as per the IS code, the maximum permissible reinforcement that is allowable in a beam is 4% of the cross sectional area, that is 0.04 B into capital D. Okay, so essentially what we are trying to do is, in question number 6 we considered an under reinforced section, and then we considered a balance section. So we are going to provide the maximum permissible steel reinforcement that can be provided in a beam as per the IS code, and it is going to be definitely an over reinforced section, and then we are going to compare the moment curvature behavior or the flexural behavior. Okay, that is what we are trying to do over here. Then for this, again I have taken the same steps in order to perform the moment curvature analysis. So first we are going to determine the value of m and phi corresponding to a value of 0.005. So I think we can go go ahead with the Excel sheet for now. So everything remains same except for the value of AST. So now it is 4500, right? So it is 4% of the cross sectional area. Then assume a value of 0.0005, right? And the value of CC is high, so we need to reduce the value of X. So the participants can suggest me the value. Okay, so we need to increase it marginally, and yes, for a value of 218.2 I got approximately equal values of the resultant compressive force and the tensile force. Okay, so and the corresponding value of moment is 112.16 and 2.29 into 10 to the power minus 6. Okay, 122. Yeah, so the I think option C is right. Yes, option C is the correct answer. Okay, and as we did with the previous problems also, we need to determine the value of moment and curvature corresponding to concrete strain of 0.0005, 001, 0015, 002 and 0035, and we get this value, we get this moment curvature plot. So in the next slide we are going to compare the moment curvature plots for the beams given in question 6, question 13 and question 16. Okay, so yeah, I think this gives us the entire story of what we have been discussing from the beginning of the class up to this point. So as you can see, this blue curve corresponds to an under reinforced beam, and this red curve corresponds to a balanced beam, and the green curve corresponds to an over reinforced beam. So we know that when it comes to the moment behavior, I mean when it comes to the moment capacity, let us call it as beam 1, beam 2 and beam 3. So if we look at the moment capacity, let me write down the curvature capacity, that is the ultimate curvature. So as we are increasing the area of steel, right, so basically we are increasing the area of steel for under reinforced, balanced and over reinforced beam. So what is happening, like the moment capacity B1 is greater than, equal to or less than. How does it compare with beam 2?
Is less than.
Yes, yeah, thanks for the answer. So B1 is less than B2 and also B2 is less than B3. Okay. On the other hand, when we consider the curvature value, the curvature of B1 is much higher. It is almost 2 times higher. That is it is able to. So what is curvature? So curvature is the value of this. If this is I'm sorry, I made a mess, but I request you to just ignore it. If this is epsilon c, if this is epsilon s, so this is the value of curvature. Okay, so it is able to rotate almost 2 times when compared to. So if you design a beam very very nicely with due consideration to its curvature and ductility, it will deform even more significantly. Okay, so whenever we are subject a beam is subjected to extreme loading conditions such as earthquake or wind or a blast loading, okay, so we need the beam to deform very significantly. Okay, so here B1, the curvature of B1 is greater than B2 and B2 is greater than B3. Okay, so especially when it comes to countries like Japan is always a favorite case study, because it is subject to all kinds of natural disasters, whether it is the wind loading or whether it is the earthquake loading or whether it's the tsunami. So we need to, whenever we are considering the design of structures for resilience, for resilience towards natural disasters, we always need to consider its deformability. So that is why using this slide, I think if we have to take all the slides from the beginning of the class to this particular slide, I think this is the most important one, which just signifies as to how much important the value of the curvature study is in while we are evaluating the flexural behavior of beams. Okay, so yeah, so to sum up, in this particular class interactive session, we considered the singly reinforced beam, okay, and we did not consider any axial load. So in the next live interaction session, we are going to consider a doubly reinforced beam, and we are going to consider the effect of axial load also. So what happens if in addition to a doubly reinforced cross section, what will happen to the moment curvature behavior when we consider the axial loads also. Okay, So I hope we understood the crux of the today's live interaction session, and I have one more question is there. So that is basically what we discussed previously. What happens to the moment and curvature, moment capacity and the curvature capacity of a reinforced concrete beam as we increase the area of steel reinforcement? So the moment value might increase, but also we need to consider the curvature value, which is equally important, which is reducing as we increase the value of steel reinforcement. So always we need to achieve some kind of parity, and always when we are designing for resilience against disaster, the better the curvature of the beam, the more desirable is its performance. Okay. Again, these are some of the results from the lecture slides, and I thank you all for your patience and for your attention. And if there are any questions, please feel free to ask me.
Thank you so much, sir.
Yeah, thank you for the for attending this session. And if there are no questions, I look forward to meeting you all again in the next week.
Okay, sir.
Yeah, thank you so much. Good night.
Now